Now we're going to talk about short field operations. Let me tell you why you need to master short field operations. Just like soft and rough field operations, you need to learn these techniques to pass your FAA check ride. But the biggie to me is that those intriguing soft and rough fields that make flying light airplanes such an adventure tend to be short too. Let me tell you about the video. I assume that you have studied videos 1 and 2 and 3, and if you haven't, I strongly encourage you to watch them first. I also assume that the runway is hard and smooth so we can focus just on short field operations. And since the Cessna 152 is the most common trainer in the U.S., we'll use it for examples. Let's talk about landings first. I'm going to assume that you will be landing at a short field with a 50-foot tree that you have to pass over. It's always a 50-foot obstacle at the end of the runway. That's sort of a standard. It's the way all the manuals are written, so that's what we'll do. There it is. Like a normal landing, you'll use some power, about 1500 RPM and full flaps on short final, but pass over the obstacle at 1.2 times stall speed in landing configuration versus 1.3 times stall speed in landing configuration. And that would be 54 knots indicated airspeed as you pass over the obstacle. Smoothly close the throttle past the obstacle while pitching down to maintain the 54 knots. Touch down on mains first to protect the nose wheel, but without trying to hold it off. That way you can start braking center. Before you start braking, lower the nose wheel, then brake hard, pull back all the way on the elevator and retract the flaps to maximize the downforce on the brakes. If you don't brake hard as you pull back on the elevator, you'll just lift the nose off, making your brakes less effective, and when you get on the brakes, it'll bang the nose wheel on and be hard on the airplane, so just don't do it. Now the takeoff is pretty straightforward too. Once again, I assume a 50-foot obstacle. A Cessna 152's best angle of climb is 55 knots without flaps and 54 knots with 10 degrees of flaps. Without flaps, almost all light planes will climb at a steeper angle than with flaps, but will require a longer takeoff roll. So to clear a 50-foot obstacle in the least distance, 10 degrees of flap takeoff shortens the roll to more than offset the shallower climb. The procedure for a 152, which is typical of light airplanes, is to use all the runway available, lower the flaps to 10 degrees, hold brakes until at full power, release brakes and accelerate in a slightly tail-low attitude, rotate, meaning pick up the nose wheel at slightly above stall speed, 50 knots, stall speed's 43, hold the VX pitch attitude, and climb at 54 knots indicated airspeed until clear of all obstacles. Retract the flaps and climb at normal cruise climb, which is 70-80 knots. So how do you compensate for the conditions? Two important factors influence short field performance: density, altitude, and wind. Density altitude is air density expressed in mean sea level altitude. An airplane responds to air molecules. The airspeed indicator measures the number and momentum of air molecules entering the pitot tube. So an airplane that stalls in landing configuration at 43 knots at sea level with 29.92 inches of mercury and 15 degrees Celsius would stall at 43 knots indicated airspeed, the same indicated airspeed in other words, at 10,000 feet and 30 degrees Celsius. The point there is you fly the airplane by the airspeed indicator and don't worry as far as maneuvering the airplane is concerned, controlling airspeed and so forth, about what your true airspeed is, what the outside air pressure is and air temperature. For all of this to make sense, we need to go into the various airspeeds and altitudes used in aviation. I do that in the next video, Advanced Landings and Takeoffs at High Altitudes. Just to motivate you, let me point out that the Cessna 152, loaded to its maximum and flown by a superbly trained test pilot, needs 1,190 feet to clear the mythical 50-foot obstacle at sea level, and 0 degrees Celsius, which by the way would be a density altitude below sea level, and it requires 4,195 feet, in other words 3,005 feet more take to clear the same obstacle at 8,000 feet mean sea level and 40 degrees Celsius. In both cases, the pilot rotates at 50 and climbs at 54. So how do we compensate for these conditions? The best way to compensate for altitude and temperature is to do what the manual tells you to do. That's always good advice. You'll find the same thing is true for compensating for wind. You'll benefit from knowing some principles, however. The greater the headwind, the shorter the distance to the obstacle can be. The 152 manual says to decrease the distance by 10% for each 9 knots of headwind. But the greater the tailwind, the longer the distance to the obstacle must be. In this case, the 152 manual tells us to increase the distance by 10% for each 2 knots of tailwind up to 10 knots. Now, without saying so, I think they're telling us that we would be crazy to take off for the purpose of clearing an obstacle with more than a 10-knot tailwind, and I'm inclined to agree with them. So you have learned short field takeoff and landing techniques on a level hard surface runway, how to calculate required distances when compensating for altitude, temperature, and wind.